So we have our invariance file. We have our target contract here, but we want to make sure we call this in a sensical order. For example, hey, don't call redeem collateral unless there is collateral to redeem, right? Maybe we want to set this up. So we're going to create a handler, which is going to handle the way we actually make calls to the DSCE. So it's basically going to, instead of us just randomly calling redeem collateral, we're only going to be able to call redeem collateral if there is collateral to redeem, right? Because otherwise the transaction is just going to revert, and that's a waste of a function call. So now we're going to create this handler. And instead of our target contract being the DSCE, our target contract is going to be this handler, which handles the way we make those calls, okay? So we're going to do SPDX license identifier MIT, as you already know. Pragma, Solidity, 0.8.18, a little caret, contract, handler, like this. And then we're going to say this contract handler is going to be test as well. And this is definitely some advanced code here. So don't get too discouraged if it doesn't make sense or if it's hard the first time, okay? So we're going to import test from forge std/test.sol. Remember to ask questions and use the forums. So what's one of the first things we want to do? Hey, don't call redeem collateral unless there is even collateral to redeem, right? We want to make sure that this is a valid run. Hey, only call redeem collateral when there is collateral in there. So this function, this contract is going to do that for us. We do need to make a constructor though, so that this handler contract knows what the DSC engine even is, right? Because it's going to be the one making the calls to it. So we do need to import the DSC engine from //src/DSC engine.sol. We also need to import the decentralized stablecoin from the decentralized stablecoin.sol constructor. And these are going to be the main functions. These are going to be the main contracts that our handler is going to call. So we're going to say DSC engine DSCE, and then we're going to say decentralized stablecoin DSC. And in the constructor here, we're going to say DSC engine underscore DSC engine and decentralized stablecoin underscore DSC. And then we're just going to say, oh, cool. It already added it. DSCE, DSC engine, and DSC is underscore DSC. So because these are the contracts that we want the handler to handle making the calls to. Great. Makes sense. So let's talk about this redeem collateral, right? Let's just focus on making this not revert. So we're going to say, okay, call this when you have collateral. So the first thing we probably need to do is what? Probably deposit collateral, right? So we'll create a function called deposit collateral. And this function is going to look a little different than the deposit collateral in the DSC engine, right? If we look in here, this is what it does. But we're going to set this deposit collateral function up in our handler so that this transaction always goes through, right? It doesn't revert. But we do want to keep the randomization, right? We want it to deposit random collaterals that are valid collaterals. So what we can do is we can create a uint256 collateral seed and a uint256 amount collateral. And this is actually really similar to the fuzz tests. So in your handlers, whatever parameters you have are going to be randomized. So we're going to pick a random one of the valid collaterals to deposit, and we're going to pick a random amount of collateral. Now I'm going to write this function without any guardrails, and it's going to break, and that's okay. We're going to fix it as we go along. But if we were to just not have any guardrails on this at all, we would just say dsce.deposit collateral, and we would do collateral and an amount collateral. We could actually just have this be address collateral and amount collateral, and we'd say deposit this collateral and amount collateral. And this, of course, is probably going to break a lot, right? Because the collateral we're going to pass is going to be wrong. This is a random address. There are so many addresses. And the amount of collateral could also break because deposit collateral reverts on 0, right? But I do want to show you what we're actually going to do in our actual contract here. Instead of having our target contract be the DSCE, what we're going to do is we're going to say handler. So we're going to import this handler. So we're going to do import handler from /handler handler.t.sol, handler. We're going to say handler equals new handler, DSCE and DSC. And now we're going to say our target contract is just the handler. Okay. Excuse me, the address handler. Now with this, the handler only has this one function. So we're going to call deposit collateral through the handler, which is going to call our engine. And since this is the only function for it to call, this is all we're going to see if we see our invariance break. So if I do forge test-m, paste this in, we're going to see it break almost instantly with an issue, but it's only going to be deposit collateral because it's the only function that we have, right? We run it again. It's still going to be deposit collateral because it's the only function the handler has. Yes, makes sense? Okay, cool. Hopefully it makes sense. In our foundry.toml, we could say fail on revert is false. We could run this again. Let's make this a little bit lower, 128. And let's see if we get any valid runs, right? Let's see if we pick miraculously a valid address and we get success, but oh, it looks like we did do some valid ones, but we've got a ton of reverts here. We've got so many reverts here that almost half of these runs, almost half of these calls were bad. That's not a great use of our, and this isn't really super helpful because of course our invariant here is going to hold because the only thing we've allowed our system to do is deposit collateral, right? Ridiculous. So if we turn this back to true, we run this again, we're of course going to break now because some of these deposits are going to fail, right? So it looks like if we call deposit collateral with some horrible address, it fails, right? So that's one of the first things we want to have our handler do. We want to say, hey, you're only allowed to deposit valid collateral. So what we can do in our handler is we can set that up. Hey, you're only allowed to deposit valid collateral. Instead of passing any address as collateral, we'll say uint256 collateral seed, okay? And what we're going to do with this seed is we're going to have it pick from our two collaterals. We're going to have it randomly pick either WETH or BTC. So we're actually going to create a function, helper functions. We're going to say function underscore get collateral from seed, uint256 collateral seed. And we're going to make this a private view function that's going to return an IERC20. Actually, we're going to do an ERC20 mock, and I'll explain why in a bit. We got to import that. Import ERC20 mock from at Open Zeppelin contracts mocks slash, what is it? Mock ERC? No, ERC20 mock.sol. Cool. And so what we're going to do instead of this line is we're going to use this line, this function to do it. We're going to say if collateral seed modulo 2, because we only have two collaterals, equals 0, then return WETH. We can get WETH by sticking at the top. We'll say ERC20 mock WETH, ERC20 mock wrapped Bitcoin. And right in our constructor, we can get all of our collateral tokens. Because I made a function way down at the bottom here called get collateral tokens, which returns the full array of collateral tokens. If you don't have this, feel free to pause and implement this. But what we can do, we can say address array memory collateral tokens equals dsce.get collateral tokens like this. And we can say WETH is 0 and wrap BTC is 1. So that's how we can get those collateral tokens. So WETH, wrap BTC. If collateral seed divided by 2 is 0, return WETH. Otherwise, return wrapped BTC. So now we have a function where we can only get a valid collateral type. So instead of just depositing any collateral type, we can say ERC20 mock collateral equals get collateral from seed, collateral seed. And now we're still depositing a random collateral, but this is, oh, it's going to be address. But this is a valid collateral address. So we're probably more likely to actually pass a transaction that will actually go through, making us have more solid, more good random calls. So let's try to run this function now. Great. successful, but we ran into an error, right? Let's see what the error is. So deposited collateral, UN256, UN256 with this huge collateral seed and nothing. So it looks like we failed here. Let's clear. Let's rerun it with dash VVVV so we can see a little bit of output of why we actually failed. Okay, the only function we're calling is deposit collateral. Looks like this failed again. We called deposit collateral with some weird args. We can scroll up and see exactly why we failed. Oh, we ran into this. DSC engine needs more than 0. So it looks like we tried to deposit 0 collateral. Amount collateral was 0. Yep. Okay. So we tried to call with 0. So amount collateral was 0. So we know that this is going to fail. So how can we make it so that this doesn't fail? Or maybe you're like, hey, like sometimes it will be 0, like whatever. I just want a sanity check. You can make fail and revert false, right? And we can run this again. And now we'll see how often this actually fails. Hopefully we cut down on the amount of times it failed. Oops. Let's remove those V's. Great. It does look like we cut down on the amount of reverts we got. Not a lot, but we did cut down on the amount of reverts, at least by adding this bounding of the collateral types. But let's keep cutting down on these reverts and potentially even have revert on false be true, right? You're not always going to have revert on false be able to be true. And sometimes it's quicker just to have it false and write all your invariants and stuff. But if you want but it is good to aim for this. Now, the downside of always aiming for this is that if you make your handler too specific, maybe you'll actually narrow it down and remove edge cases that would break the system that are valid, right? So it's kind of this balancing game you have to play with these fuzzing tests and whether fail and revert to be true or false. There's definitely a little bit of an art to this. So the more you do it, the better you'll get. But in any case, collateral seed, amount collateral, we need to now change it so that this amount collateral is bounded between 1 and some max number, right? So we don't want this to be able to be 0. So what we can do then instead is we actually can bound this so that in the same way we got a valid collateral, let's get a valid amount collateral. So we can say amount collateral equals bound. This is a function that actually comes with std utils and it bounds the result to an amount. So we want to say, okay, this amount collateral, we're going to bound our amount collateral to being between 1, we don't want it to be 0, and then some like really, really big number. What I like to do is up here in the state variables, I'll do UN256 max deposit size equals, and I'll do type uint96 dot max. And this allows us to get the max uint96 value. Why are we not doing the max uint256? Well, if we do the max uint256 and we try to deposit more collateral later, if you do the max uint256 plus 1, you'll get a revert. So this is going to give us a really, really, really big number, but we're at least not going to hit the absolute top of amount of deposits we can deposit. So we're going to say we're going to bound this amount collateral between 1 and max deposit size. Okay, cool. So let's put this back to false. Let's run this test again, and let's see if we cut down on the reverts some more. Aha, a couple more, right? Only a few hundred, but we did cut down on the amount of reverts. Why? Because we're passing valid, well, okay, that one didn't go so well, but we are cutting down on the amount of reverts piece by piece. We're able to bound the collateral, but there's more. If we do fail on revert back to true, we can see exactly why it's failing, right? We'll do dash VV. We can see an example that is indeed failing. And whoa, these are getting more intricate, right? Before it was just a single call was breaking it. Oh, okay, so a single call still is breaking it, but they are getting a little bit more intricate. So it looks like this one failed because what? We called deposit collateral. We scroll up, we're getting this insufficient allowance. Oh, okay, so that's why we actually weren't cutting down on the reverts at all, because we're getting insufficient allowance. Of course, we need to approve the protocol to deposit this collateral. So of course this is breaking. This is always going to break. So let's do a little prankage. So we'll do vm.startPrank. We'll just do message.sender, and we'll allow this message sender to mint some of this collateral so that they can actually deposit it, right? So we can set this up so that whoever's calling deposit collateral actually has the collateral and actually will approve to deposit the collateral. So, and this is why I'm using this ERC20 mock so that we can actually mint some of this collateral. So we'll do collateral.mint, message.sender, amount collateral. We'll do collateral.approve, address DSCE for the amount collateral. Then we can deposit it, and then we'll do vm.stop-prank. Okay, now let's clear this. Let's have revert on false to be false. And let's see now if we cut down on the amount of reverts that we get. Oh, and I added too many V's. Let's get rid of those. Let's run this again. And yep, there will be some brief delays in here, of course. Whoa, we cut the amount of reverts down to 0. Now, all of our function calls are passing, which means every single run was a valid run, meaning we're using our runs much more wisely. We're not wasting runs on failed reverts. So now I can even set this to true, run this again, and we'll see this passes and none of our runs failed, right? So this means, what does this mean from a security standpoint? It means that no matter how often we call deposit collateral, no matter how much we deposit our collateral, we will never make this invariant false, which isn't saying too much because, of course, we're not even, the total supply is always 0. Of course this holds. So this makes a lot of sense. So let's actually keep writing more functions to do more with the system, but set them up so that whenever we call them, they're always going to be valid calls. Okay.